also Michael wanted me to ask you if you were willing to email him stuff you needed to know for the test so he could come up with some example problems to go over for different numbers or just topics. But he told me to ask that, so don't shoot the messenger.
Okay. Look at the old tests.
Okay, that's what
I mean, he
okay.
should have access to
Right, okay.
all the old tests except for, I guess, except for the test that I've given since I last sent him the list.
Okay, perfect, thank you.
Or I've sent him master sets, I've sent him, I'll double check. I'll try to remember to double check. All right, so let's just go through an addition of vectors problem. Let's say I've got a positive and negative charge, an electric dipole, as it were. And the distance between them is, let's say 10 centimeters. And that distance will make 4 centimeters, and that distance, say 6 centimeters. What's the electric field at that dot? Well, I know that each charge gives off, has an electric field that it either gives off or absorbs. So the electric field from the positive charge goes in which direction at this point? All right, we got a couple of figures pointing in the right direction and a couple not. All right, got one corrected. Does it go away or towards positive charge?
Away.
Yeah. All right, so there should be basically a straight line there, and that's the electric field in that direction. We'll call it E plus. And let's just deal with that one to start with. No, actually, let's get the other one. And the negative charge, in which direction is the electric field at that point from the negative charge?
It's going towards the negative charge.
All right. Which of these vectors actually should be bigger? E plus or E minus?
E plus,
Why?
because it's closer.
Yes. It's closer, therefore it's a larger magnitude. And so let's just, I don't know the relative strengths at the moment, but at least have some pseudo sense of realism. So the total electric field at this point is the sum of these two vectors. I can do a crude sketch here. That's supposed to be a parallelogram. And so the total vector will look something like that. That's my total electric field. But there's a certain amount of guesswork in it, so we need to come up with something more analytical. So let's first take a look at E plus. Let's establish a coordinate system, I hat and J hat. So how do I find the magnitude of the electric field at this point?
You take the components from each of the electric field vectors.
Wait, say that again?
You take the components from each of the electric field vectors.
Not define just this. You jumped ahead a few steps.
Oh.
How do you find the magnitude of an electric field from a point charge?
Would you add like the positive and
KQ2R over R squared?
Say, I felt like, I wasn't sure if you were saying extra letters or correcting yourself as you went.
No, K times QR No, K times Q squared. No, Q1, yeah, that one point of charge over R squared.
So you've settled on KQ one over R squared?
Yeah.
Okay, yes, that's how you do it. So the magnitude, K Q positive over R squared. So 9 times 10 to the 9th. My charge here, make it 3 nanocoulombs and 3 nanocoulombs, yeah, 3 nanocoulombs. So 3 times 10 to the negative 9th. Divided by the distance squared. So I basically need to know this physical distance right there. Well, I conveniently have a right triangle where that length is 4 centimeters and this length is 6 centimeters. I don't even have to find the exact length of that. All I need is R squared. And Pythagorean theorem tells me that 4 squared plus 6 squared is, that's R, is equal to R squared. Let's call it R plus. So that's 16 plus 36, 52. If you want, you could actually find the value of R and then square it again. The number of times I've seen that, and suddenly this number right here is different than the number here because I'm rounding. So we end up with 27 over 52, which is some absolutely spectacular number, which will make your life better. What are the units?
Newtons per coulombs?
Like you need it.
Newtons per coulombs.
There we go. Because if I multiply it by, if I put a charge here at this point, if I multiply it times the electric field, I can have newtons would be the force acting on it. So that's the number of newtons that will be exerted per coulomb that's sitting there. It's 413. That's as reduced as that fraction can go without going to decimals. Having a particularly foggy day today. All right, so now the direction. Well, I know physically that's 4 centimeters, that's 6 centimeters, so I could use a little trick to figure out what that angle is. So I know the tangent of theta is 6 over 4, or theta is the arctan of 1.5. And if someone would be kind enough to tell me what the arctan of 1.5 is.
56.31 degrees.
Thank you. All right. So what we have here. So I have this vector here which represents 2750 seconds, newtons per coulomb. And this angle right here is 56.31 degrees. Now, I have a hypotenuse and an angle. I can break it up into components right here and I can think through. So let's just go ahead and do it that way and then I'll show you a different, slightly different way. So horizontal, vertical, this is the adjacent side. So this is going to be 2750 seconds times the cosine of 56.31 degrees. That's this. And that's the opposite side. So that's going to be 2750 seconds times the sine of 56.31 degrees. And what do we get?
For cosine, it's gonna be 0.288.
238?
288.
288. All right.
Sine is 0.432.
So given the way I've defined I hat and J hat, what is my electric field in rectangular form?
It's positive 0.432 nanocoulombs J hat and negative 0.288 nanocoulombs I hat.
Now, Daniel expressed it in the reverse order. He did the J hat first and then the I hat. Nothing wrong with that. I'm a creature of habit here. So if he had done it, flipped it around with this term first, still good. Now, we could have done it slightly differently because in polar form, remember polar form, from your point of view, 0 degrees is this way and then 90 degrees is up, and so forth until you get to 360 degrees. I know that this angle here is 56.31 degrees, but if I want to put this in polar form, I want to know that angle. And what would that angle be? It's properly marked, they should have a different number of lines there. What is this angle?
180 minus 56.31 is 123.69 degrees.
So in polar form, my electric field, positive electric field, is 27 over 52 newtons per coulomb, 123.69 degrees. That's polar form. If you put down 56.31 degrees as the angle in polar form, that would be a first quadrant angle, but we're second quadrant. So if it's in polar form, there's a very thought-lacking way of doing it. You have to still have to remember it. But this would be 27 50-seconds newtons per coulomb times the cosine of 123.69 degrees I hat plus 27 over 52 newtons per coulomb times the sine of 123.69 degrees J hat. Now, don't leave it in that form, but if you multiply all this together here, you'll get negative 0.288, unless there's a Carol's error somewhere. Negative 0.288. The minus sign's gonna, this is a negative number here. And then the other one should be 0.432. Now, we could have done this, we could write this slightly differently. Some students like just writing, you come up with your answer and then you just slap the units on at the end. I will say that if you wrote negative 0.288 I hat plus 0.432 J hat newtons per coulomb, I would actually take points off of that. That newtons per coulomb, the way this is written, is only associated with the second term. If I wanted to associate with the first term, let's do parentheses. Anyway, that's my E positive. Questions? All right, let's do an E negative. Now the juices are flowing. How do we find the magnitude?
KQ negative over R squared.
Yep. So the magnitude of E negative is 9 times 10 to the ninth times 3 times 10 to the negative ninth divided by, all right, so we now need to figure out what r squared is. Well, what is that distance?
6.
Ooh, there's a mistake over there. Anyway. Actually, let's just stop it right here. What is the mistake over here? When we found E positive?
Should be Coulomb. Oh, wait, no.
What's wrong with, you said unit?
Yeah, units,
What's wrong with the unit?
or in centimeters, not meters.
Yeah, it just sort of hit me. This right here is centimeters squared. This is 0.04 meters, 0.06 meters. This would be 0.0052 centimeters squared. Just make sure that's right. So that would be 0.16, 0.36, so 0.52. No, that's not right. That was right the first time. So 0.04 squared plus 0.06 squared, point 16. Yeah, plus 0.0036. Unless I made another careless error.
Say, for some crazy example, we were in inches instead, what would the units be?
I would put it into metric. Yeah, and 2.54, and this is an exact this is an exact conversion. 2.54 centimeters equals 1 inch. Set forth by the gods of units. All right, so we have an extra 4 decimal places there, so 1, 2, 3, 4. So 2,880 and 4,320. And I've erased the mistake over there, so that doesn't exist. All right, I think we are, I assume somebody just double checked my math. It is 0.0052, right?
Yes.
Okay. Did any of you spot the mistake before I actually stopped and mentioned it?
I mean, I saw that you were doing in centimeters, but I didn't know that was actually what you mentioned.
That kind of mistake would have been 2 points off on a 10-point problem. Because ultimately, the process was completely right, just units were wrong in the end. All right, so divided by, okay, so back to the question I was asking, what is this length right here?
6 centimeters.
So we end up with an r squared value of 0.0072. And what mythical and magical number do we end up with?
3,750.
And what the heck, we'll throw units into it.
Newtons per Coulomb.
All right. Now we're cooking. We need to figure out the angle. Well, if I can figure out that angle, I can easily find the angles up there. So what is that angle? Without a calculator. And it's been 3 minutes, it's not a Massachusetts calculator. Oh,
120, would it be 180 minus the 53?
Yeah.
The angle we found?
think about the triangle we're working with here. This is my triangle right there.
It's a 45-degree angle.
It's a 45-degree angle, 6 and 6. So this angle here is 45 degrees. So if I want to put this in polar form, I need that angle, so 225. So my E negative is equal to 3,750 newtons per coulomb and 225 degrees. That's polar form. We can put it into rectangular form just by this times the cosine I hat, this times the sine of that j hat. So 3,750 newtons per coulomb times the cosine of 225 degrees I hat plus 3,750 newtons per coulomb times the sine of 225 degrees j hat. And what do we get?
For cosine, it's gonna be negative 2,651.65.
2,000, say it again, 2,600.
651.65.
Oh, and minus 2,651.65 newtons per coulomb j hat. It does have a symmetry. So the total electric field, well, I've got, is just the sum of those two vectors. So there's my E negative. My E positive is negative 2,880 newtons per